Hello everyone! Today I will present our paper, a precise framework for source-level control flow analysis. My name is Idris Riwak, and this is a joint work with Christoph Reichenbach, Jorel Edin, and Niklas Forsch. Data flow analysis play a very important role in software development and is used to detect subtle bugs such as null pointer dereferencing and data assignment. We are doing source-level data flow analysis. This means that we build a control flow graph on top of the AST, and this because it might simplify the integration with an integrated development environment, and because the report can be directly linked to the source code. Doing the analysis at the source level has significant consequences. For example, every time that we want to support a new language, we must take into consideration the large engineering effort. Secondly, the syntax, therefore the AST, doesn't always reflect the program semantics, and this is the case for initializers and exception handling in Java. In our approach, we build control flow graph as an extension of the AST, using reference attributed grammars. The entire specification of our work is declarative. We have been able to handle implicit control flow, and we overcome the limitation of the earlier framework. Here, I reported some of the research questions that we asked ourselves. For example, how can we reduce the engineering effort? How can we fill the gap between the syntax and the semantics? And if our new approach is competitive both in performance and precision. We removed the limitation of the previous RAG-based framework, JastAdd INTRAFlow, and we will explain how using this simple example. On the top left corner, we have a while statement with a condition and a post-increment expression. Right below, we have the AST representation of this snippet, and in light blue, the successor relation. JastAdd INTRAFlow builds parent-first control flow graph. That means that every time we want to visit a node, for example P1, we always have to visit its parent first, in this case the less operation. This approach has two main problems. The first problem is that the control flow graph includes redundant nodes, that are nodes that doesn't have any semantic value, or which value is already embedded in the control flow graph. The second and more severe problem is that the control flow graph includes misplaced nodes. Therefore, the constructed control flow graph doesn't always reflect the real execution of the program. Our framework, INTRACFG, builds AST-Unrestricted control flow graphs. This means that the control flow graph doesn't have to follow the nesting structure of the AST, allowing us to create control flow graphs that reflects the real execution of the program. INTRACFG is a RAG-based and language-independent framework. It defines three different interfaces: CFG root, CFG node, and CFG support. The framework provides a default behavior for each AST node that implements one of these interfaces. Then we implemented INTRAJ. INTRAJ is an application of the INTRACFG framework and is implemented as an extension of the extendj extendable Java compiler. To validate the precision and the performance of INTRAJ, we implemented three different data flow analyses: null pointer analysis, live variable analysis, and data assignment analysis. In this slide, we are reporting the number of lines of code of each module. As we can see, we have been able to reduce the engineering effort required to support the Java language by exploiting the default behavior provided by the framework. Now, I will explain the role of each interface in the framework using the following example. In this snippet of code, we have a method foo with three parameters and a conditional assignment. As we said before, INTRACFG provides three different interfaces: CFG root, CFG support, and CFG node. CFG root is intended to be implemented by all the AST nodes that represent a subroutine, for example, method declaration and constructor declaration in Java. All the CFG root nodes extend the AST with two higher order attributes, entry and exit, that actually represent the unique entry and exit point of the control flow graph. I will soon explain what an higher order attribute is. The CFG support nodes are nodes that are not part of the control flow graph, but are essential to create it. In particular, a CFG support node has two main attributes. I will use the block nodes to explain what these attributes compute. The first node's attribute for the block node computes the first CFG node inside the subtree rooted in the block node. Similarly, the next node attribute points to the first CFG node outside the subtree rooted in the block node. Nota bene, the attribute next node is a set of CFG nodes. This because a CFG support can have multiple next nodes. The same thing holds for the first node's attribute. Then we have that all the CFG nodes are CFG supports. We exploit the first and the next node attributes to compute the successor relation. Once we have the successor relation, the predecessor is computed as the inverse of the successor. One of the main challenges of constructing the control flow graph on the AST were to make explicit all the implicit facts. We used higher order attribute, a reference attributed grammar mechanism, to extend the AST with new subtrees. We used higher order attribute to make explicit the call to close method for all the resources inside a trie with resources. We refined static and instance initializers. We reached exception sensitivity by refining the chain of finally block. And finally, as a corner case, we refined the implicit condition in an empty for loop. Once we have constructed the control flow graph, we implemented data flow analysis with mutual dependent equation. In fact, attributes may depend on its own value. In this case, the attribute will compute a fixed point. As said before, we implemented 3 different data flow analyses: null pointer analysis, live variable analysis, and dead assignment analysis. In this presentation, we will take into consideration only null pointer analysis. The analysis is defined for each CFG node, and it computes 2 mutually dependent attributes, in and out. Each of these attributes compute an abstract environment gamma. Gamma maps access path to element in the binary lattice L2. The in attributes collects and merge the contribution from all the predecessor, while the out attribute is the result of the application of the transfer function on the evaluation of the in attribute. On the right, we have 2 implementation examples. The first one is the default definition of the transfer function for all the CFG nodes. The second one is the overridden definition for the assignment expression. We have performed 2 different studies on INTRAJ. In the first, we compared the size of the control flow graphs constructed by INTRAJ and the ones constructed by JastAdd intraflow. The second study compared INTRAJ's performance and precision against the industrial static checker SonarCube. We have also compared the performance and the precision against JastAdd intraflow, but that can be found in the paper. We evaluate the tools on 4 different open source projects: Enter, PMD, JFreeChart, and FOP. The first result that we are reporting is the drastic CFG size reduction. We have been able to reduce the control flow graph size of the 30 and in some cases 43% by removing all the redundant nodes. This enables faster client analysis. For the precision, we consider dead assignment analysis and null pointer analysis. We denote in green the number of true positives and in red the number of false positives. As we can see, for dead assignment analysis, INTRAJ performs definitely better than SonarCube, as it is able to report more true positives. Moreover, as we can see, SonarCube reports 8 false positives in PMD and 44 false positives in FOP, while INTRAJ reports only 1 false positive that is also detected by SonarCube. Let us now consider null pointer analysis. Here, INTRAJ is able to report at least as many reports as SonarCube, except for PMD, where SonarCube reports 3 more warnings. The false positive reported by INTRAJ are due to the lack of path sensitivity. Moreover, we have to take into consideration that INTRAJ runs an intraprocedural analysis, while SonarCube runs a more precise interprocedural analysis. For the performance, the first thing that we can notice is the difference between the baselines. The baseline measures the execution time for each tool without any analysis enabled. We think that SonarCube computes more things in the baseline that INTRAJ attributes to the analysis. Knowing that, for dead assignment analysis, INTRAJ is lower than SonarCube, but remains competitive, while for null pointer analysis, INTRAJ is definitely more performant. To conclude, we presented INTRACFG, a language-independent RAG framework that overcomes the limitation of the earlier approach. we have been able to reach high precision. We reduced the CFG size of at least 30%, and we saw that we can reach high performance also for large code bases. We also presented INTRAJ, an instance of the INTRACFG framework for the Java language. We kept the specification of INTRAJ and of the client analysis concise by exploiting the default behavior provided by the framework. And finally, we saw that our approach is competitive with industrial tools such as SonarQube. Thank you very much for your attention.